All right, it's 8 o'clock, so we're going to get started. Welcome to your first live stream. So this is the basic setup. You'll log on, I'll send you a link, and then there's two ways you can interact with me on here. You guys can either, if you're logged into a YouTube account, just chat right on the live page. That's totally fine. I'll see your chats pop up on my chat window. Or you can just use Remind. I don't mind that either. So just send me a Remind at whatever time. I will respond back to you. Remember that you're maybe 30 seconds behind me lag. So if I don't get to it right away, I will get to it soon. We're going to do probably about 45 minutes-ish tonight. And you can always rewatch this. So if you get interrupted, that's fine. It lives on YouTube forever until we take it down. So we're going to get started. So your test is on 1-1 through 1-6. Those are our first 6 units or 6 lessons, and that really covers most of pre-calc. The big thing that I want you guys to remember is the reminder I sent you earlier, which was that I gave you the wrong review sheet. So I will drop off another one to your first block teacher tomorrow for you guys. But these are your basic things. You want functions, domain, and range, polynomials, rationals, exponentials, log, and trig. So those are your 6 main things that you're looking for. We are just going to go through example problems. If there's anything else you need more help on or more specific questions, just send them my way and we'll do that, okay? So we're going to start basic and we'll kind of work our way through. So this first one says, which of the following represent functions? And you've got 4 different representations of functions here, or of relations at least. I need to figure out if they're functions. So I'm going to start by just kind of go through each one. Remember that a function is like when you have the movie theater, each input only goes to one output. One input, 2 inputs could go to the same output, but not the other way around. So I'm going to look at each of these individually. So for this first one, I see that I've got 2 going to 6, and I've got 2 going to -6. Knowing that 2 is going to 2 different outputs, not a function, right? Next one, I have a graph, or actually let's look at number 2. So here I have a set of points. I've got, let's look at my inputs. 1, 2, 3, 4, 5, 6, 7. None of those inputs repeat, so there's no chance I'm going to have one input going to 2 outputs. So this one is definitely a function. The next one, number 3, well, that is not passing a vertical line test. Remember, that's how we would check and see, not a function. And 4, that's the equation of a line. Linear functions are functions. So this would be 2 and 4. All right, the next one, finding domain and range. So this gives me this graph and asks me for the domain of it. I definitely see that it's not all real numbers. So I know that much at least. But when I look at this, let's kind of see what we've got. So first of all, I see that it's not a function. Definitely not a function. It has points that would not pass a vertical line test. But at least for this relation, let's see what we can get. So I see that this is definitely an interval, right? It's not just a set of points. So I'm going to either be using the idea of sort of the brackets or parentheses or interval notation. So it starts at -2. It goes all the way to -1. -1 is included. It jumps up and goes all the way to 0. 0 is included. So far, I've had no break from -1 to 0. Even though there was a jump discontinuity there was no break in the domain, just a break in the range. Now, going from 0 to 1, again, there's no break in the domain because those are both closed circles. But there is a break in the range. That's okay. Going over to here, I have that open circle, so it's not defined at 1 on that piece, but it is defined at 1 on that piece. So again, even though there's a break in the range, there's no break in the domain, so that continues. Going to here where I have an open circle at 2, and so I'm going to have an open circle at 2, so I have an open half of that interval. Now, none of my answer choices here are in this notation. So I would expect at this point that you can move fluidly between these notations. It's definitely not a list, so I'm going to get rid of 1 and 2. Those braces are used for a list, right? So it's either 3 or 4. I know that it has to be 3 because of that open endpoint on the right side. Okay, continue to send me questions if you have them. Let's look at this one. This one's kind of funny. So which statement about the function f of x equals x minus 3 over x plus 2 is true? And we have things about the domain and we have things about the range. And now this is a rational function. So I need to think really closely about this. So let's start with the domain. Where would this be undefined? Well, anywhere there's a hole or a vertical asymptote, it's going to be undefined, right? Now, I can't reduce this anymore, so there are no holes. But there is a vertical asymptote. Vertical asymptotes happen when the bottom is 0. So this has a vertical asymptote, or as we are going to start calling it, an infinite discontinuity at x equals -2. And that's the only point that's not in the domain. So my domain should be that. So I know that it's not 1 and it's not 2. So this must have to do with the range. Now, figuring out the range is a little trickier. The only thing I can really figure out with this range here is going to be what my horizontal asymptote is. Because if I've got this horizontal asymptote, wherever it is, we're going to kind of approach that from both sides, and that value is not in my range. So, looking at this, I'm going to look at the behavior of it. So the numerator, the degree is 1, that's your dominant term. The denominator, your degree is 1, so that's your dominant term. So your horizontal asymptote here is y equals 1, because it's 1 over 1. So I know that it would not cross that line because my end behavior is approaching that line on either side, right? So I know that that is not in my range. Okay, let's move on to some symmetry. And same thing as always, keep sending me questions if you have them. So I want to complete this function or this graph to make an odd function. That's my goal. And I know that this much is true. So odd function, remember that this needs to be symmetric over the origin, or about the origin. I guess about would be a better word there, which means that it has 180-degree rotational symmetry. So symmetric about the origin. So it means when I turn it upside down, it should be exactly the same. Now, if it goes up like this, it's got to be symmetric but beneath the axis there. So it's going to come down to here and then go back up. And what I notice is if I actually inverted that, so let's actually do some creative drawing here. If I actually took this and I inverted it, or spun it, it's not really an inversion, but if I actually took this and spun it around, it should map directly on top of that. So that's how I know that that's an odd function. All right, next one, complete this to make it an even function. Well, even should make you think symmetric over the y-axis. So it's already got this half. I need that to really be a reflection over the y-axis, so it's going to look like that. And again, it should look reflected over that. We'll talk more about functions like this that have those cusps in them in our next unit, but odd versus even, one of those important things we need to know for this test. All right. Next one, which of the following is even and how do you know? So here's what we need to think about. We need to think about what happens when you evaluate f of -x. So it's either going to be all the same and it's even, it will be all opposite and it will be odd, or it will be a mix and it will be neither. And so that's really what I'm going to look at. So let's look at this first one. So f of -x would equal the square root of -2x minus 1. Now, is that the exact opposite of what we started with? Nope. Is that the exact same? Nope. So this is neither. Let's look at the next one. So if I use this one, I'm going to find f of -x, which would be -4x cubed plus 8x plus 2. Notice that this one changed, but the other two did not. That is a big old neither. So we're hoping, for our sake, it's the last one, right? And I'm not just trying to trick you. So let's check. F of -x. Well, when you take the absolute value of -x, it's still just going to be the same as absolute value of +x. Plus, when you square a negative, it's still positive. And the 7 is a constant, so that doesn't change. So this one is even because f of negative x equals f of x. That is my even one, that third one. All right, so let's look at some polynomials because that was the next topic we hit on. So, big thing that I want to talk about with polynomials is end behavior. And remember, this is different than symmetry. This is talking about the degree, not the symmetry of it. So, even degree. The simplest function you can think of with an even degree should be maybe x squared. And if I think of positive x squared, it looks like that. If I think of negative x squared, it looks like that. That is what I call my end behavior model here. For an odd degree, the simplest one I can think of is x to the first. The simplest one I can think of for a negative is negative x to the first. So that's my end behavior model for that. So here's what I'm going to say on this one. As x approaches infinity, which would mean as x goes to the right, y approaches infinity, y goes up. Same thing here, as x approaches negative infinity, so as x goes left, y approaches positive infinity because it goes up. So that doesn't change, okay? Now let's look at what it would be for the next one. So for this one, and again, I expect this notation, no up-ups, down-downs, we're too sophisticated for that. This one, they're both going down, so in both scenarios, it would approach negative infinity. For the next one, let's look at this graph, and I'm actually just going to paste this in both places. So for the next one, I'm going to look at this. To the left of that line, it's going down when I look down here. To the right, it's going up. So as x goes to the right, y goes up towards infinity. As x goes left, y goes to negative infinity. And for this one, to the left, it goes up. To the right, it goes down. So as x goes to the right, y goes to negative infinity. As x goes to the left, y goes to positive infinity. So that's what I'm looking at for my end behavior models. And we're going to use that as we go into some of these polynomial questions. So let's take a look at this one. Without using a calculator, use that function for each question below. So first thing it asked me is to describe the end behavior. So my degree, my highest exponent is 3, and my leading coefficient is positive. So this is going to behave like a positive odd power, which is going to behave like x to the first. So that means as x goes towards infinity, p of x, notice I'm not saying y, I'm using the function they gave me, that goes towards infinity. And as x goes towards negative infinity, p of x goes towards negative infinity. On this, if you said y, you would be incorrect because we're not talking about y here, we're talking about p. So be very specific and name your functions if they give you a name. All right, let's find the roots. So to find the roots, we're going to set this equal to 0. So 0 equals x cubed minus 5x squared minus 4x plus 20. And I'm going to factor that. So I'm going to factor it by grouping. So group your first two, group your second two. I'm going to take out an x squared. That's x minus 5. I'm going to take out a negative 4. That's x minus 5. And so this becomes x squared minus 4, x minus 5. Now, x squared minus 4, I can factor further. So that's x minus 2, x plus 2, and x minus 5. So you've got 3 zeros, which makes sense. You have a third degree. And that's going to give me x equals negative 2, positive 2, and 5. Now, intervals of positive and negative behavior. Now let's look at this. We can only change from positive to negative if we're crossing a 0, right? So I'm going to make myself a little sign chart. I'm going to put my zeros on there. And don't forget that the intervals on the outskirts of your zeros are still intervals. So I'm going to look at this factored form, and I'm going to see what happens when I plug in numbers here. So let's start in this region. So let's say I plug in negative 3. Well, this would give me a negative, and a negative. And so that's going to give me all negative. So this would be negative in this region. Now, the next one, let's say I go between negative 2 and positive 2. 0 is probably an easy one to do there. So this would give me a negative, a positive, and a negative. A negative, a positive, and a negative multiply to give you a positive. continue this interval will give you negative, that interval will give you positive. Now, a really smart thing to notice here would be look at our multiplicities. All of our multiplicities are 1, which means this actually crosses at every single one of those points. So if you know that this side is down and you know it's crossing at every 0, then you could be able to go down, up, without having to actually test every region. But if you need to test, there's nothing wrong with that, okay? Now, I didn't answer the question. It says find the intervals. So what I would say here is that P of X is positive when, or on the intervals, let's say that, on the interval from -2 to 2 and the interval from 5 to infinity. And I would say P of X is negative on -infinity to -2 and 2 to 5. That's really the answer that I want to see. This other work is important, but that description part is really the big mama there. All right, and now the last part says sketch a graph. So I'm going to start with putting my zeros. I'm just going to label them. And I'm going to shrink this down a little bit so I have some space. By the way, if you're going to college and you have an iPad, look into the app Notability. That's what this is. It's the greatest thing that's ever happened. So I have 1 0 at -2. I have 1 0 at +2. And I have a 0 at 5. And I know my end behavior should go down on this end and up on that end, right? Now I'm going to kind of connect those. So I know it starts negative, switches to positive there. It's going to go here. So I'm kind of connecting those. And this should be smooth. I'm drawing on an iPad, so bear with me. And then that should do the same thing there. And then it should go up. Okay? Basic sketch. I'm not asking you for all the other important information about it, but a basic sketch of that shape. Now, the other thing is make sure it's smooth and continuous, right? Polynomials don't have any corners, any discontinuities. They should be nice and smooth. All right, send questions if you have them. Otherwise, I'm going to keep going on a roll. All right, let's talk rationals. Find horizontal asymptotes, infinite discontinuities, and removable discontinuities. Horizontal asymptotes, hopefully we know, okay, what that word means. Infinite discontinuities is vertical asymptotes because we are infinitely not meeting. And removable discontinuities is a hole in the graph, okay? So let's look at each of these. For the first one, let's start with horizontal asymptote. For horizontal asymptote, I'm going to think about what's growing faster. Or I'm going to look at the degree of my numerator and the degree of my denominator. My numerator is a constant. It is not growing. My denominator is an x squared. That's definitely growing faster. So think about it. If the bottom of a fraction gets bigger, that whole fraction should approach 0. So this should be y equals 0. If you just put 0 there, you've not given me an asymptote. Remember, an asymptote's a horizontal line here. So you need the y equals. All right, let's talk about infinite discontinuities or vertical asymptotes. These happen when the denominator equals 0 and factors have not canceled, right? Now, I'm going to say, can my denominator equal 0? Well, if I do that, I get x squared equals -1. So I get x equals plus or minus I. My denominator can equal 0, but it cannot equal it, over the real number system. And so this is not going to be on my graph. So there are no infinite discontinuities. And removable discontinuities. So let's look at those. That's where a factor cancels in the top and the bottom. Nothing cancels here, so there are none. Okay, next one. Let's look at this one. 2x plus 1 over x plus 1. So, first of all, if we can factor, let's factor. Can we? No. Okay? 2x plus 1 is prime. X plus 1 is prime. We can't fix those. Can't factor them more. So, let's start with horizontal asymptote. Look at your degrees, okay? So, this is my dominant term in the numerator. That's my dominant term in the denominator. Those have matching degrees. So, I'm just going to divide my leading coefficients. So, y equals 2 over 1 or 2. All right, infinite discontinuities or vertical asymptotes. Let's think about these. Can my denominator equal 0? Yeah, I can. X plus 1 equals 0 at x equals negative 1. So I have one vertical asymptote, and it's there. And then the last part, removable discontinuities, is any holes. Did I have any factors cancel? I did not, so there are none. All right, last one of these. I've got this baby, and there's even some factoring with a leading coefficient of 1. So let's start by factoring this. So I'm going to take my numerator and deal with that. If this is something you don't feel comfortable factoring, come see me before the test or look up a video on YouTube, because this is something you need to know how to do. So you can either use guess and check, that doesn't bother me, or you can use the AC method and do split the middle. So I'm going to multiply A times C, that gives me 6. And now I'm looking for two numbers that multiply to be 6 and add to be negative 2. So multiply to be 6, add to be negative 2. Can we think of any? Well, I've got 1 and 6, or I've got 2 and 3. Can you think of any other integers that multiply to be negative 2? Or that multiply to be 6? I can't. Neither of those would combine to be 6. So this is not factorable. That numerator is not factorable over the integers. So I can't simplify that at all. So vertical asymptote, or sorry, let's do horizontal asymptote. Dominant term up here is that. Dominant term down here is this. The top is growing faster. And so if I think about that, that fraction's just going to keep growing. So this has no vertical asymptote because the numerator is dominating. Now, infinite discontinuities. Can the bottom equal 0? Yes, when x equals 1. Removable discontinuities, there is nothing that canceled, so this would have none. Now, because I didn't put one in here that actually had one, let's do a quick removable. So let's say I gave you x minus 1 over x squared minus 1. Okay, so first thing I would do is factor it. I would say that this is an over x minus 1, x plus 1. So these could cancel out. So this would have a horizontal asymptote. Well, look at your degrees. Top, bottom. The bottom is dominating, so that would approach 0. The infinite discontinuities, when you cancel, that's left over. So x equals negative 1. And the removable discontinuities, those canceled out, right? So that would be at x equals positive 1. To get the y value, you plug back in. So what's left over here after you cancel is 1 over x plus 1. So if your removable discontinuity is at 1, plug that back into this, and that would give you 1 over 2. Okay. Let's talk about this. This was a new thing. So describe the behavior of the functions near their vertical asymptotes. So we're going to think about vertical asymptotes. We're going to test numbers a little bit on either side and think about what happens there, okay? Now, vertical asymptotes, it's always going to approach infinity or negative infinity. We just want to decide which one. So let's look at this one. This would have a vertical asymptote or an infinite discontinuity at x equals 3. And I'm going to test a number on either side of that because I know at x equals 3, that's undefined, right? So I just want to know, is it going up forever or is it going down forever? Okay? So I'm going to look at this, and let's plug in a number a little bit to the left. So if I plug in a number a little bit to the left, let's say 2.9, that would give me 2.9 minus 3, which is negative, but I'm taking the absolute value, so that whole fraction comes out to be a positive. If I plug in a number a little bit to the right, well, absolute value is always going to be positive, so that's positive. So what that tells me about the graph is if my vertical asymptote's here, it's going to go positive, positive on either side of that. The way I would want you to write this is, as x approaches 3 from the left, notice this is y, so I would say y approaches positive infinity. And as x approaches 3 from the right, y approaches positive infinity. So this is what I'm talking about when I mean describe the behavior. Okay, we're going to do one more of those, then we'll do some logs. So m of t, I know I should be talking about m in my answer. So where are my vertical asymptotes? Well, nothing cancels. I actually have 3 vertical asymptotes here. This would equal 0 at t equals 0, and this would be at plus or minus 2. So let's take a look at these. So negative 2, 0, and 2. And I almost like to do these as like 3 little segments so I don't get confused about being, in one, because I want to look at a number very close to each one. So let's think about negative 2. Let's say I plug in a number a little bit smaller than that. So maybe here I think about like negative 2.1, right? So this absolute value will always be positive. It almost doesn't matter. This numerator would be negative, and the denominator, absolute value, is positive, and this piece would be positive. So you would have, for that, negative over positive times positive. So just to the left of negative 2, you're going to get a negative number. Now let's look to the right of negative 2. So let's say we plug in negative 1.9, right? So that's definitely going to be negative in the numerator. This absolute value is always positive. But now that t squared minus 4 is going to be negative. And so I get a negative over a negative. So that is positive there. So I would start by summarizing this and saying, as t approaches negative 2 from the left, m of t approaches negative infinity. As t approaches negative 2 from the right, m of t approaches positive infinity. So that takes care of that first vertical asymptote. We've got 2 more to analyze though. So let's look at these. So now let's talk about 0. Okay, let's talk about 0. So by 0, let's plug in a little bit to the left. Let's say negative 0.1. That would give me a negative over a positive times a negative, which is definitely going to give me a positive. Let's say I plug in a number a little bit bigger than that. I plug in 1.1. That's going to give me a positive over a positive times a negative, which would be negative. So for this one, I would say as t approaches 0 from the left, m of t approaches positive infinity. And as t approaches 0 from the right, m of t approaches negative infinity. Now let's do the last one of these. So let's say I look at 2. So maybe here I think about plugging in a number like 1.9. That's going to give me a positive over positive times a negative. So that will give me a negative overall. Here, let's say I plug in like 2.1. So that would give me a positive over a positive times a positive. So that would give me a positive overall. So then I could say as t approaches 2 from the left, m of t approaches negative infinity. And as t approaches 2 from the right, m of t approaches positive infinity. You did a whole Khan Academy on this. So if you need to go practice this more, go back and just redo it. I'm not taking another grade from it. Just practice it again. Okay? All right, my way. We're going to start logs in about 30 seconds after I take a drink. But send any questions my way, either on Remind or on the YouTube chat. Okay. So let's start with logs. You won't have a calculator, so you need to be able to evaluate a log. So for this first one, log base 16 of 4. So what I'm saying to myself is, what power of 16 gives me 4? Well, 4 is the square root of 16, so that should be 1/2. Now this one's kind of funny. It says ln of e to the negative third. Well, remember ln is really log base e there. So this is funny. I'm saying e to what power is negative third? So look at what I'm really saying. E to what power is e to the negative third? That makes it much more obvious when you rewrite it that way. This is negative 3. All right, let's do a little converting. This is the basic skill here. So log base 3 of 15 equals x. So my base is 3, right? And I'm going to go around to there. That's my exponent because logs are exponents. And then come back around, and that is 15. Converted. Done. This one is in exponential form. So blank equals log blank blank. Now, logs are exponents, so it's always going to equal the exponents. Okay? Now my base is 4, and the number I haven't used yet is 64. And last one, ln of 2x plus 1 equals 5. Remember your base is e, so you're doing e to the 5th power equals 2x plus 1. Okay, let's do some properties. Condensing, expanding, stupid dances. Ready? When you multiply, you add, right? Or when you add logs, you can multiply. When you subtract logs, you can divide. Or when you divide, you can subtract the logs. When you raise a power to another power, you can multiply. Or when you raise an argument to a power, you can multiply. So let's look at these. So log base 3 of c minus log base 3 of a plus log base 3 of b. Starting in my parentheses, I see add, so I'm going to multiply. So this is really log base 3 of ab. And now I see subtraction, so that's log base 3 of c over ab. That is condensed. In your head, if you can go straight to that step, that's fine. You don't need to show me all those intermediate steps, okay? All right, next one. That power out front goes up as an exponent. So this would be log x to the 5th plus log y to the 4th. And remember, if you just see log, your base is 10, right? It's unwritten, but it's there. Now I see addition, so I'm going to multiply. So log of x to the 5th, y to the 4th. Done. All right, let's go the other way. So now I'm giving you this, and I want to expand it out. So I see multiplication. I'm going to add. So log x plus log y to the 5th, or you can bring that down to the front, plus 2 log z. Done. And last one, and this is important, you're multiplying these together, right? So this would be log base 8 of 8 plus log base 8 of a. And then you're dividing by that, so minus log base 8 of b cubed, which you could bring that down to the front and make a 3 there. Now, if you put parentheses here, that wouldn't be wrong. That would be okay. You could even go further and say log base 8 of 8 is 1 plus log base 8 of a minus 3 log base 8 of b. This form and this form, one's not more right than the other. That one's just further simplified down. Okay, so exponential and logs, we're not going to go through this whole chart right now. But if you feel like you're struggling with log and exponential equations, this chart's in your notes, and it tells you exactly what to do when. The basic idea is exponential, usually you're converting into a log. Log, usually you're converting into an exponential. The exception is if you can create a common base, you're done with exponents. You just set the exponents equal. And if there's logs on both sides, you can just set the insides equal, the arguments, okay? So let's solve each equation here. We're going to do these pretty quick. If you have questions, send them to me, okay? So let's look at this one. Log base 4 of n equals log base 4 of 8. I have log base 4 of something equals log base 4 of something. I hope that that screams to you that n has to be 8. Okay, next one. Log of 2x minus 1 equals 3. So I'm going to get the log alone. So I'm going to do log of 2x equals 4. Remember that I have an unwritten base of 10 there. There's nothing else I can do to this log right now. So now I'm going to convert. So 10 to the 4th equals 2x. So that's 10,000 over 2 equals x. So x is 5,000. All right, next one. This is an exponential. There's nothing I can do to simplify that. All the algebra is up in the exponent. So I'm going to convert it to log form. So blank equals log blank blank. Logs are exponents, so the exponent goes on the equal sign. Your base is 3, and 7 is what you haven't used yet. So now, I'm just going to erase these so they don't confuse us. I'm going to get that alone. And it's a good idea here maybe to put the 7 in parentheses. So first thing I'm going to do is add 3. So 2x is log base 3 of 7 plus 3. That's not log base 3 of 10. And then divide everything by 2. So my answer is x equals log base 3 of 7 plus 3 all over 2. It did not tell me to round, so don't. That's exact form. Just leave it there. All right, next one. Same idea, except on this one, I can get my bases to match because 36 is a power of 6. Now, solving this the way we did the last one would work, but we can actually make our lives a little faster and easier here. So here's what I would do. I would say that 36 is 6 squared. So instead of doing 36 to the x minus 1, I'm going to do that. And this is 6 to the first. Now here I'm raising a power to a power, right? Right here. So I can multiply those. So this is 6 to the 2x minus 2 equals 6 to the first. And so that gives me 2x minus 2 equals 1 because my exponents need to be equal. And so 2x is 3, so x is 1.5. All right, let's do a couple more. 11, I think we're okay on. Let's look at 12. So 12 looks ugly. So what you need to do here is use some of your log properties. So let's start by simplifying this as much as we can. So log base 3 of 2 to the 4th minus log base 3 of x squared equals 1. Now I see subtraction, so I can divide. So log base 3 of 2 to the 4th is 16 over x squared equals 1. And now I'm going to convert. So this would be 3 to the first equals 16 over x squared. Cross multiply that. So 16 equals 3x squared. Divide both sides by 3. X squared equals 16 over 3. And then square root both sides. So I get x equals plus or minus radical 16 over 3. Now, the argument of a log, the inside part, cannot be negative. So we're going to not look at that negative solution. So x would be the square root of 16 over 3, or you could say 4 over radical 3. All right, let's do another one. Let's look at 13. So, again, properties of logs. These are being added, so I'm going to multiply them. Now, I have log on both sides, which means the arguments need to be the same. So x squared minus x equals 12. Solve that. I would get x squared minus x minus 12 is 0. Factor it out. And so I get x equals negative 3 or x equals 4. Now the argument of a log can't be negative, so it cannot be that, so that's my only solution. All right, last one of these. ln, just put your base e there. This is already in log form, so e to the 5th equals 3x plus 4. I'm going to have to subtract 4 and divide by 3. So I would wind up getting e to the 5th minus 4 over 3. Again, if you need help on these, let me know, okay? Or check out your notes, check out that flowchart. All right, last thing is trig. Let's do this. So here's what I want you to brain dump on your paper. Number 1, I want you to brain dump your little all students take calculus. Number 2, I want you to brain dump sine cos, pi over 6, pi over 4, pi over 3. And then make your chart 1, 2, 3, 3, 2, 1. Put everything over 2. And then square root the tops of everything, or at least the 2's and the 3's, right? All right, so let's do a couple of these. So sine of pi over 2. Well, pi over 2 is right here. That is quadrantal. And so I need to use that coordinate, which is 0, 1. Sine is the y value, so this would be 1. Cos 11 pi over 6. So that is a little bit less than 12 over 6, which would be 2 pi, so that's down here. So in that quadrant, cosine is positive. And my reference angle there is pi over 6. Cos of pi over 6 is radical 3 over 2. Tan 5 pi over 4. 5 pi over 4 is a little bit more than 4 over 4. And tangent is sine over cosine. So this is going to be radical 2 over 2 over radical 2 over 2. Divide those. You're dividing something by itself, so that's just 1. And in the third quadrant, tangent is positive. All right, next one, cosecant 4 pi over 3. So let's start with where that is. That is 1/3 of the way past 3 over 3. So that's in the third quadrant. Sine there is negative, so cosecant will be negative. So let's do sine of 4 pi over 3. It is negative, and then sine of pi over 3 is radical 3 over 2. So this is 2 over radical 3. I'm cool with leaving it that way. All right, secant of 5 pi over 6. That is in this quadrant. So now we're looking at cosine there. Cos is negative. So cos of 5 pi over 6 is negative, and then cosine of pi over 6 is radical 3 over 2. It's the number of the day. So this would be negative 2 over radical 3. All right, and then cotangent of 5 pi over 4. Well, tangent of 5 pi over 4 was 1. So cotangent is going to be 1 also. But let's think about where 5 pi over 4 is with that negative sign in there. So that's going this way now. So I'm actually going to wind up in the second quadrant. And there, tangent is negative. So this is going to be negative 1. All right, last thing, identities. You need to have these 11 identities memorized. Not kind of know, memorized. With the bottom ones, remember you need to know that one, and you can derive the other two. But I would write that down at the very top of your paper so you're not in the middle of the test trying to go back and do that, okay? So brain dump it. So let's do a couple. We're not going to do a ton of these because we did a lot of these today. But if you need more examples or you need more help, shoot me a message. So let's start with, I'm going to start with this first one on the left. And I'm picking this one for a very specific reason. I see ones and I see squareds. And whenever I see a 1 and a squared together, I hear fire alarms and bells and whistles in my head. I think, okay, probably a Pythagorean. So let's look at 1 minus cos squared. Let's go up to our Pythagoreans. If I move this one, so the cos squared goes over to the right, that would leave me with just sine squared there. And notice I'm writing sine squared x, not just sine squared. Now, same thing in the denominator. I've got secant squared x minus 1. So secant squared, if I subtract this 1 over, that just leaves me with tangent squared. And none of those lazy arrows I saw in class, okay? You really want to write this out. So this, actually simplifying it, I would do sine squared x over sine squared over cos squared. And from there, I can do sine squared times cos squared over sine squared, which makes these cancel. So I'm left with just cos squared equals cos squared. That, to a mathematician, is the most exciting part of the proof, which I know is kind of like an awkward statement, but that's where you've proved it, right? So don't like sell yourself short and leave that out. Put that in there. That's important. All right, let's look at another one. Let's look at 3, because this one might have some more interesting stuff in it. So here I've got sine times tan plus cos equals secant. Whenever I'm not sure what else to do, transform everything to sine and cosine. So sine, I'm going to leave as sine. Tan, I'm going to make sine over cos. Plus cos A. Now, this gives me sine squared, and that should be an A, over cos plus cos. To add those, I need a common denominator. So remember that this is over 1. So what I'm going to do is I'm going to multiply this one by cos A over cos A to get my denominators to match. So that gives me sine squared A plus cos squared A over cos A. And I see some squareds. I'm thinking Pythagorean. That's 1 over cos A. And my goodness, look what we just proved. 1 over cos is secant. The most exciting part, we proved it. All right, let's do one more good one. Let's do 6. Okay, 1 plus sine over cos plus cos over 1 plus sine. I need to add these, so I need to get a common denominator. So I'm going to multiply this one by 1 plus sine and that one by cos. So this gives me 1 plus sine squared plus cos squared over cos times 1 plus sine. Let's simplify. 1 plus sine squared, you actually need to like FOIL out. So 1 plus 2 sine theta plus sine squared theta plus cos squared theta. So here what I did was 1 plus sine times 1 plus sine over cos times 1 plus sine. And now here's what I'm looking for. Sine squared plus cos squared is 1, right? So this is actually going to be 2 plus 2 sine theta over cos theta times 1 plus sine theta. Now, I could factor out a 2 there. Beautiful things happen. Those cancel. So I get 2 over cos. And 2 over cos is the same as 2 secant. So 2 secant equals 2 secant. Again, if you need more help on this, come talk to me and let me know. But that's it. That's what's going to be on your test. So I'm going to hang out for about a minute because there's not a ton of people on live still right now. But if you have questions, let me know. If you're watching this on a replay, send me questions anytime. Test is Monday. I'm at school at 6:30 on Monday, so feel free to get there early and just go over stuff. And I wish you guys good luck. Have a good weekend. But again, I'll hang out for a couple minutes if you have questions.